Okay, welcome back. We're going to go over adding vectors using the head to tail method and then make our way into projectile motion or two-dimensional motion. All right, so if we are going to add vectors, there's two different scenarios in which we would need to do that. One is if the vectors are parallel to each other, and the other is if they're perpendicular to each other. So we're going to do the easier method first, and that's if they're parallel. So again, we're going to obey what we call the head to tail method. So here we have this first vector, and here we have a second vector, and we want to add those together. Now, you are allowed to pick up and move a vector around any way that you see fit, so long as you don't change the orientation of the vector or the size of the vector. So I can move this top vector here down so that the tail of this vector is to the head of this vector. The head is the arrow part, of course, and the tail is the part without the head. So I would have something that looks like this. So the resultant vector then is going to be a vector that is from this end all the way to this end. All right, that's them added together. So something that looks like that would be our resultant vector when we add the previous two. Okay, we could have this situation up here where the vectors are still parallel to each other, but now they're pointing in opposite directions, whereas the previous two vectors were pointing in the same direction. Now the previous two vectors were pointing in the same direction as they went to the right, okay? But we could just as easily have had where both of those vectors are going to move to the left and still be facing the same direction, okay? And we would still add them the same way, head to tail. All right, so in this case, we're still going to add these two vectors head to tail. So I'm going to take the head of one vector, which would be like this right here, and put it to the tail of this vector. So those are lined up there, okay? And we're going to move in opposite directions, and so that means we're really, basically we're going to be subtracting here, okay? So we want a vector that is going to add up to look like this. That would be our resultant vector there, okay? All right. So now let's look and see what happens if we have vectors that are perpendicular to each other. Okay, if our vectors are perpendicular to each other, then we're going to have to use some trigonometry to figure them out. And that's going to be right triangle trigonometry. Now, some of you may be in geometry right now, or maybe you're in pre-cal. And so you've already gone over this a little bit before, and that's okay. This is just going to kind of be a refresher. If you haven't, then this will be good for you. All right, so the first thing that we want to look at is, where is theta? Theta is the angle that we know, all right? Of course, we know 90 degrees here, and then we have theta. Up in this corner, we also have another angle that we could know, and a lot of times that one's called theta prime, or sometimes this one down here is called alpha, angle alpha, and this one up here is called angle beta. It all, can be called whatever. It really doesn't matter. You just have to understand that the sides of your triangle here are named based off of the location of the angle that you know. Okay, so I know this angle theta, and the side that's located opposite of that angle is called opposite, and the side that's located right next to that angle is called adjacent. And then, of course, as always, the longest leg of a triangle is the hypotenuse. Okay, but these sides here are always named for the angle that you're referencing. Also, in your calculators, you need to always be in degree mode if you're going to be typing in sine, cosine, or tangent, which is the trigonometric functions. Okay, so we have SOHCAHTOA. All right, and let's just kind of briefly go through what that means. Okay, SOHCAHTOA says that the sine of theta is equal to the opposite side divided by the hypotenuse side, okay? And that's the lengths of those sides, or the magnitude of those sides, okay? The cosine of theta is equal to the adjacent side over the hypotenuse side. And the tangent of theta is equal to the opposite side over the adjacent side. Okay? So any of those trigonometric functions, sine, cosine, or tangent, is going to give you your opposite over hypotenuse, adjacent over hypotenuse, or opposite over adjacent. You can solve for any of these unknowns here, okay? Now, these things here are responsible for solving for the sides of a triangle. If you want the angle of a triangle, then you're going to use the inverse of them, okay? That means that theta is equal to the inverse sine, okay, of the opposite over the hypotenuse. Okay, theta is equal to the inverse cosine of the adjacent side over the hypotenuse. And theta is equal to the inverse tangent of the opposite over the adjacent side. Okay, so the inverse of these trigonometric functions gives you your angle. The normal trigonometric functions give you sides. Okay, so please make sure that you know that. So how does all of this lead back to adding up perpendicular vectors? Well, let's see here. Let's say that I have this ship right here, and that ship is going to travel 7 miles to the east, and then 2 miles south, then 5 miles to the west, then 6 miles north, and then finally 3 miles east before the ship runs out of gas and has to stop. So we got a radio in to the Coast Guard, who's back here at home base, all right, the origin, and we got to tell them how to get to us without having to follow this big ridiculous path here, because then they would run out of gas and then we wouldn't have any help, right? So we want the shortest distance between 2 points. So what we're going to do is we're going to condense all of the east-west stuff, and we're going to condense all the north-south stuff. All right, so if I go in there and look at this, I've got 7 miles to the east, okay, and I've got 5 miles to the west, okay? So to the east, that's positive. To the west, that's negative. That means so far I have overall a positive 2, all right? So I'm going to say, let's see, 7 minus 5, and then I've also got 3 miles to the east, so plus another 3. So overall, that's 5 miles to the east. So if you look over here at our new picture, we've gone 5 miles to the east. Now let's do the north-south, or the up and down stuff, okay? So I have 2 miles south. Since it's south, that's negative 2. And then 6 miles to the north. And then there's no more north-south stuff. So that means overall I have positive 4 miles. So if you look at our new picture over here, we've gone up 4 miles. All right? This is the head-to-tail method, okay? So the x-axis, I have a vector that comes out here, and there's the head. And then I'm going to take the tail of the next vector, the y vector, and put it against the head of the previous vector. So head to tail. And then I come out here, and this is where the boat stops. Now I need to know what this resultant vector is. In other words, the shortest distance between the starting point and the ending point. Okay? So we're going to do Pythagorean theorem to figure out what the magnitude is of that vector. All right? So, of course, the Pythagorean theorem is telling me that a squared plus b squared equals c squared. And we're going to say that the a squared is the x, so that's going to be your x displacement. We'll say the b is the y, and then c squared is the resultant vector, okay? That means what happens when you add these two previous vectors here together, okay? So we don't want the resultant vector squared, however, we want just the resultant vector. So we need to take the square root of both sides. So that means the resultant vector is equal to the square root of x squared plus y squared. So that's going to be the square root of, let's see here, our x piece is 5 and our y piece is 4. So 5 squared plus 4 squared. So the square root of 25 plus 16. Okay, and so then we're finally going to have about 6.4 as our magnitude there. Okay, 6.4 miles. Now that is just magnitude. Well, if it's a vector, we need direction because vectors have magnitude and direction. Okay, and this piece right here, this is just the magnitude. So the direction, let's see how we're going to get that. If we come back up here and look at our picture here, we can see that there's an angle theta right here, and that angle theta is the direction. Okay, so the length of this, or the magnitude of this line here, that's the magnitude of the vector, and then this theta, this angle from 0, is going to be your direction. And we got to know how to figure that out. So remember, everything on this triangle is named based off of theta. So this is the opposite side, okay, because it's opposite to theta, and this is your adjacent side because it's the one right next to theta. Okay, so what are we going to use? If we know what the opposite side is, because we just figured out, that's 4, and we know what the adjacent side is, that's 5, then how can we solve for theta? Okay, well, hopefully you remember from the previous slide that theta is equal to the inverse tangent of the opposite over adjacent. So that's what we're going to use. We're going to say that theta equals the inverse tangent of, the opposite side was our y-axis, and the y-axis one was 4, and the adjacent side was our x-axis, and that one was 5. So we're going to say 4 over 5. Okay, so when I do that, I'm coming up with 38.659 blah 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 degrees. Okay, now in this class, and you should actually, all other physics classes, unless your teacher tells you otherwise, you only need to have 3 sig figs for angles. So remember that you want to look one place value further than the last digit that you're going to keep, just for rounding purposes. So does this 5 do anything to that 6? Yes, it does. So then our theta, our angle, is going to be 38.7 degrees. Okay, now we need to assemble this into a final answer, okay, because right now we don't have a final answer. So what we're going to do for that final answer is we're going to say the resultant vector is equal to 6.4 miles at 38.7 degrees. Okay, that is our final answer. Okay, now let me give you a quick note about this angle here. Okay, when you say an angle as an answer, the entire scientific community thinks that you are referencing the first quadrant. Okay, So if I put 38.7 degrees, they think that you mean 38.7 degrees right here. If you don't mean right there, then you need to be more specific and tell everybody which quadrant you're talking about using your cardinal positions. Okay, so for example, if you were talking about this angle right here, if you mean that this is 38.7 degrees, then you would need to say that that is 38.7 degrees west of north because you moved towards the west away from the north. All right, so west of north. If you mean that this angle right here is 38.7 degrees, then you would say north of west because you moved towards the north away from the west. All right. If you mean that you have this line and you're talking about this angle right here, okay, and that that one was 38.7 degrees, then you would say that this is 38.7 degrees west of south, okay? If you mean this angle right here, then you would say 38.7 degrees south of west. Okay, so you just need to use your cardinal positions to describe which angle you're talking about if you're not in the first quadrant. Or, if you don't like doing all of that, okay, then you can set your angle in reference to the 0 degree line, okay? If you want, you can say, I'm going to know this angle. I'm going to talk about this angle right here. And that, since it's in relation to 0 degrees, you can just say the angle and leave it alone. You don't have to put any other cardinal directions at the end of it. So if we know that from here to here is 180 degrees, and we know that from here to here is 38.7 degrees, then all you have to do is add 180 plus the 38.7 degrees, and you would say that this angle here is 218.7 degrees, right? So if you were going to do a final answer and you didn't want to have to write, south of west, okay, then you could just put this angle in instead and just leave it at that. Now, of course, we want to do that with only 3 digits, so instead of saying 218.7, that would be 219 degrees, and you would be done, okay? That's if, of course, you are not in the first quadrant, okay? If you're in any quadrant but the first one, then you need to either use your cardinal directions or you need to give us the angle in relation to 0 degrees if you want to just state the angle and leave it alone. One more thing that I want to talk about is if you're down here in this fourth quadrant, okay, you can subtract away from 360, okay? We know that if you were to go all the way around the circle, that'd be 360. You can back up by an amount and come up with your angle in relation to 0, okay? So like if we have this angle right here, let's say it was like 15 degrees, then you could say 360 minus 15 degrees, okay? And if you do that, that's going to tell you how many degrees you would travel from 0 all the way around until you hit the line here, okay? So just got to know what your different degrees are. This is 0 and 360. This is 90. This is 180. This is 270 because each quadrant is worth 90 degrees. All right. Let's talk about two-dimensional motion, all right, or we can call it projectile motion. And this kind of breaks down into some different categories. We have horizontal projectile motion and we have angular projectile motion, okay? So horizontal projectile motion, of course, is going to be at 0 degrees the whole time, okay? Some things that we know about the object when it's got horizontal projectile motion. The velocity is going to be constant in the x-axis, okay? The acceleration is going to be 0 in the x-axis, okay? We know both of those things for sure. So what would that look like? Okay, you could have, let's see, we've got like a desk or table or something here, and there's a ball, and that ball is going to roll off of the table and land on the ground over here somewhere. Okay, that's an example of horizontal projectile motion. All right, we've got some kind of velocity in the x-axis here. That's going to be constant, and the ball is going to be falling in the y-axis the whole time. Okay, so that means that we know the initial velocity in the y-axis is going to be 0 meters per second, and we know that the acceleration in the y-axis is still going to be negative 9.81 meters per second squared. Okay, so that's some stuff we know about the horizontal projectile motion. Okay, now let's talk about angular projectile motion. This can be split into angular projectile motion with symmetry or without symmetry. Okay, so let's look at those scenarios. Okay, if we're talking about symmetry, we know that the x velocity is still going to be constant. We know that the x acceleration is still going to be 0 meters per second squared. The y velocity is going to be the original velocity times the sine of the launch angle. And we know the acceleration in the y-axis is going to be negative little g. Okay, in other words, negative 9.81 meters per second squared. Now, what would that look like? Oh, and one more thing, I'm sorry. We'll also know that delta y is going to be 0, and that the range equation applies. There we go. Okay, so what would that look like? Well, let's see. I could have a football, and let's say that I'm going to launch that football at some angle, theta, and so that ball is going to fly through the air, and then it's going to land back on Earth over here somewhere. Okay? And so if that happens, you'll notice that the ball took off from the ground over here, and it landed on the ground over here. Okay? So that means that delta y is equal to 0. Okay? And there's symmetry to this problem. Okay? If you figure out how long it takes for the ball to land over here, you can divide that by 2, and that'll tell you how long does it take the ball to get to its maximum height. All right? Or vice versa. If you know the full length of the ball traveled, you can divide by 2 and figure out how far did it go when it was at its highest point. All right? So those are some neat things that you can do if you have symmetry in your problem. So what if you have no symmetry in your problem? What are some things we would know then? Okay, we know that the x velocity is still going to be constant. We know that the x acceleration is still going to be 0. We know that the initial y is going to be the initial velocity times the sine of theta. We know the acceleration is going to be negative little g, which is negative 9.81 meters per second squared. We know that the range equation does not apply. Okay, so those are some things that we know. What would that look like? All right, let's say we have this kid here, and he's gonna shoot a basketball. Okay, and let's say that this basketball is, I don't know, 1.2 meters off the ground. And we want that basketball to land in a hoop, okay? So let's say that that hoop is up here somewhere. All right, so that basketball is going to and it's going to fly through the air until it lands into the basket, okay? The distance from the hoop down to the ground is going to be something larger than 1.2 meters. Okay, so if it's larger than 1.2 meters, then that means that the ball is going to take off from a position over here, okay, and it's going to land at a position higher than what it took off from. There are situations where you could have the ball land at a position lower than what it took off from. The point is that delta y is not 0, okay? So if you have a problem with no symmetry, then we know that delta y does not equal 0, okay? And that's why the range equation doesn't apply. And we'll talk about what the range equation is in just a minute. All right, so let's try and work a problem here. The first one we're going to try is a horizontal projectile problem. If you need to refresh yourself about what characteristics a horizontal projectile motion problem has, just skip backwards in the video and look at that. Or hopefully you're taking notes with me right now and it is on a piece of paper right in front of you. Okay, so let's go through the problem. A ball is hit with an initial velocity of 6 meters per second. Now when they say that, if they're telling you this ball is hit at a velocity of 6 meters per second and they don't mention an angle, then that means this has to be a horizontal velocity, okay? If the ball leaves the floor 2 meters above the ground, how long will it take in seconds to hit the ground, and with what velocity will it hit the ground? Okay, so we're going to go ahead and say that this ball is on a table. So we're going to draw ourselves a little picture here, and this x-axis velocity is going to be the 6 meters per second, okay, and the height of the table is going to be 2 meters. That's a tall table, okay, so that the ball is 2 meters above the ground, and the ball, we know, is going to fall out here somewhere in that parabola, that arc, okay, and we want to know how long is it going to take to do that, first of all, and then we want to know, once it strikes down here, what is the velocity with which the ball is going to strike? All right, so the first thing that you need to do whenever you have a projectile motion problem is to make a list of the stuff in the x-axis that you know and make a list of the stuff in the y-axis that you know. Okay, so we know that in the x-axis the velocity is 6 meters per second. We know the acceleration is 0 meters per second squared. we don't know how far away from the edge of the table the ball is going to land, in other words, delta x. We don't know that, and as it turns out, they didn't ask me for that, so it's not something I'm going to have to figure out. And I don't know how long it took for the ball to travel this distance right here, so I don't know anything else in the x-axis. By the way, if you're having trouble making your list, just write down what your kinematic variables are. Final velocity, okay, initial velocity, acceleration, displacement, and time. Okay. Now, since the velocity in the x-axis is constant, there's not going to be any such thing as final or initial velocity. It's just velocity. Okay, so the only velocity I know is Vx, okay, what it took off with. I know the acceleration, I don't know delta x, and I don't know t. I've run out of variables. That means this is all that I can know in the x-axis right now. Okay, now let's fill in our y-axis, and we're going to just go through the list again of those kinematic variables. The initial velocity in the y-axis is 0 meters per second. I do not know what the final velocity in the y-axis is when the ball strikes the ground. This is not the y-axis final velocity. This is the overall y-axis velocity. Okay? When that ball lands, it's going to have some velocity in the x-axis, okay, because that velocity in the x-axis is constant, and it's going to have some velocity in the y-axis, and that's going to be pointing down. All right? Now, this velocity here, that is our overall velocity. That's the resultant vector. Hopefully you can tell that that shape there is this triangle, okay? And that's our right triangle. Our angle theta is going to be this angle right here, and this is the overall final velocity that we're trying to figure out. Okay, so let's go back to filling out our y stuff. The final velocity in the y-axis is not 0, all right? The acceleration in the y-axis is negative 9.81 meters per second squared. The displacement, delta y, okay? You might want to say that it is 2 meters, but that's not quite true, okay? Remember, we're describing information about the ball, and delta means change in, final minus initial, okay? The final position of the ball will be down here on the ground, okay? The initial position of the ball was 2 meters up here above the ground. So final minus initial would be 0 minus 2. So this is negative 2. That negative sign just means the ball is falling down. So if the ball is moving down, then you need to make sure that you have a negative displacement. All right? So I can use this information to solve for time. Remember, if you have 3 pieces of information, you can solve for the other 2. All right? So that means I can solve for v final in the y-axis, and I can solve for time using my y-axis information because I have 3 other pieces of information from my kinematic variables list. All right, so let's go ahead and solve for the time using the information that I have available. I need an equation that has only these 4 variables and nothing else. In other words, the only equation that does not have final velocity in it. So I'm going to say delta y is equal to initial velocity in the y-axis times time plus 1/2 times the acceleration in the y-axis times time squared. Okay, now this piece right here goes to 0 because the initial velocity in the y-axis is 0. And we're trying to solve for time. So I'm going to multiply both sides by 2, divide by acceleration, and then take the square root to get rid of that squared. So t is equal to the square root of 2 times delta y over the acceleration. Okay? So let's go ahead and do that. T equals the square root of 2 times negative 2 over negative 9.81 meters per second squared. And this is negative 2 meters here. Okay, let's plug that in our calculators. Okay, so when I do that, I'm coming up with time is equal to 0.638550856881 blah 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 seconds. We just need to have several digits, okay? That way we don't introduce a rounding error into our results later on. Now this is an official final answer, so we need to use sig figs. So if we go back and look at our problem up here, we had 6.0, so that's 2 sig figs. We had 2.0, that's 2 sig figs. And the 2.0 one is the one we used in our calculation for time. So that means time needs to have 2 significant digits. So we're going to say then 0, because we never started a number with a decimal, 0.6, that's the first sig fig. Here's the second sig fig. We need to look one place value further for rounding purposes and see if that 8 does anything to the 3. It does, so 0.64 seconds. Okay, that's the first part of the question answered. Okay, the next part of the question asked us at what velocity will it hit the ground, and remember they're asking me for this overall final velocity here. So that means I need to know Vx, which I already do, and I need to know V final y. I don't know that yet, so I need to figure that out. I do know that we have an equation that says that V final is equal to V initial plus acceleration times time. So that means that I can just plug my stuff in, right? This piece here goes to 0 because the initial velocity in the y-axis is 0. So that means I just need to do acceleration times time. Now, when I do that, I'm not going to use this rounded time here because that would introduce some rounding errors into my math. I need to use this big long number up here. So we're going to multiply that number times negative 9.81. And when I do that, I am getting that the final velocity in the y-axis is equal to negative 6.2641839 blah 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 meters per second. Now this negative sign that we have here is because the ball is falling down in the y-axis at the end. Alright, so we can draw our triangle there for that resultant velocity vector, okay, and we've got our x-axis, okay, and we have our y-axis. Alright, now the x-axis velocity was the 6 meters per second. The y-axis velocity is this negative 6.264 number, and we need to make sure that we use every single digit that our calculator tells us, not just this little piece that I wrote. I just did that because I ran out of room. Okay, and we are trying to figure out what this overall final velocity is right here. Now, if we do the Pythagorean theorem, that's just going to give us the magnitude. But remember, velocity is a vector, which means that we have to have magnitude and direction. So we need to have this angle theta. Okay? If we go back up here and look at our picture, when the ball strikes the ground right here, okay, it's going to make that triangle like we're making below, and we need this this angle theta right here in order to have our direction. So that's the same as this angle theta right here, okay? All right, so let's do our Pythagorean theorem real quick. The final velocity is equal to the square root of the x-axis velocity squared plus v final y squared. All right? Okay, so when I do that, I'm coming up with 8.674099 meters per second. And we only want 2 sig figs because we have 6.0 up there. So that means 8.7 meters per second is the magnitude of that velocity. Now we need to get our direction. So based off of that angle theta, I have the opposite side and I have the adjacent side. So I need to do tangent. Okay, so I know that theta is equal to the inverse tangent of negative 6.26418 blah 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 over 6. Okay, and so when I do that, I'm getting theta to be negative 46.23 degrees. Now, you can't have a negative degree value, all right? So what that means is, the reason that your calculator is telling you it's negative is because they're saying that the angle is something below this positive x-axis over here, okay? It's this angle right here. So we're not going to say negative 46.2 degrees, because remember we only want 3 sig figs there for a degree. We're going to say it's positive 46.2 degrees, and then we're going to use our cardinal positions to describe what quadrant we're in, okay? So we're going to say that it is 46.2 degrees, and then we're going to say that's south of east, okay? Or if we want to go in relation to 0 degrees, we want to go all the way around, then we would just subtract this value from 360, okay? And we would say that it is 314 degrees, okay? Now we need to write a complete answer, a final answer. So we're going to say that that overall final velocity vector is equal to 8.7 meters per second at 46.2 degrees south of east, okay, or the final velocity vector is equal to 8.7 meters per second at 314 degrees. And we just leave it at that. Okay, so either of these answers here would be correct for that final one. All right, so that is projectile motion horizontally. All right, the next problem. A rocket is launched from the ground at a 30-degree angle relative to the ground with an initial velocity of 30 meters per second. Now, since they gave me this angle here, that must mean that this is angular projectile motion. And if we take a look at how this rocket would launch, okay, it would follow some path like this, and then it would strike the ground over here, okay? That's going to be with symmetry, all right? If we have this rocket launching, and I didn't do the best job drawing just then, so that's why I'm redoing that. Okay, so if I launch that rocket, then it's going to return to the Earth. So there's symmetry there. Its starting position and its ending position are at the same spot. So there's definitely symmetry. So the first thing we need to do with this problem, as we do with all projectile motion problems, is to make an X and Y list. All right? I'm going to go ahead and write in that the original velocity here is 30.0 meters per second. and we already know that that angle is 30 degrees. Alright, so my x list and my y list. Now you'll notice I'm making two y lists, and I'll tell you why in just a minute. Let's go ahead and fill in our x-axis information. Okay, if I look at this original vector here, okay, that's this one right here, it does not lie on the x-axis, which is of course this axis right here, and it does not lie on the y-axis, which is this one right here. That means we have to decompose it. We have to use our trigonometric functions to break it down into the x and y component. So hopefully you can tell that this moves out in the x-axis about this much, okay? And hopefully you can tell that it moves up in the y-axis this much. Okay, so that's the x and y component. X is purple, the green is y, okay? And the angle that I know is the angle theta, okay? And that's this angle right here. That's 30 degrees to the horizontal. That means that opposite to this angle is y, and adjacent to this angle is x. So when we do adjacent stuff, we use cosine, and when we have opposite, we use sine, right? So we're going to say then that the x-axis velocity is equal to the original velocity times the cosine of the angle. Remember to be in degree mode in your calculator. We know that the acceleration in the x-axis is going to be 0 meters per second squared. And we don't know anything else in the x-axis. I don't know delta x, and I don't know how long it took the ball to get to the end. Okay? Now, let's look at some possible questions that we could be asked. They can ask me what my horizontal velocity is, what's the vertical velocity, how long does it take the ball to come back to Earth, how far away from the original position will the rocket travel, that's delta x, what's the maximum height the rocket will reach, what is the velocity of the rocket, magnitude and direction when it strikes the Earth's surface, how is the vertical velocity of the rocket, or excuse me, what is the vertical velocity of the rocket at its highest point, what's the horizontal velocity of the rocket at its highest point, and what is the acceleration of the rocket at its highest point. Okay, whenever you make a date with somebody, okay, or you make an appointment, you have to share two pieces of information. You have to know when and where, which is why I have two columns of y information that we're going to go back to in just a second. You are being asked in letter D, or excuse me, in letter C, how long does it take the rocket to fall back to Earth? So the where is when the rocket arrives back at Earth. You're being asked to solve for the when. That means that your y-axis information that you have is going to have to be about the ball when it is back on Earth at the very end. That way you can solve for the time that it takes to get to the end. Okay? If you look at letter E, however, it's asking what's the maximum height of the rocket. Okay? That means they're telling you where the ball is. It's at its peak, and so the information that you're going to need to plug in about the ball is all the stuff you know when it is at that position. Okay, so that's why we have two y columns. One is going to be at the maximum height, and one is going to be at the very end, so that we can plug in information about the ball when it is in those two different locations. Okay, so one of the first things that it asked down there was, what's the horizontal velocity? All right, that is the 30 cosine 30 that we see here. And so that's going to give us like 25.9807, blah, blah, blah. Hopefully you're typing this into your calculator. I really want you guys to be typing this along with me and solving these problems with me so that you're getting practice as well. So 9.80762 meters per second. Okay? So in order to answer letter A with the correct number of sig figs, because it's a final answer, you'll see that our original velocity had 3 sig figs in it. We never look at angles to determine sig figs for an answer, so that means that my final answer then is going to be 26.0 meters per second, because this 8 here is going to round that 9 up to a 0, which rounds the 5 to a 6, so 26.0. The next thing that we're being asked is what is the vertical velocity? Okay, so that comes with our y list of information. And it doesn't matter which y list, because the ball always takes off from this position over here at this original velocity. So I can say that the velocity initial in the y-axis is equal to the 30 meters per second times the sine of 30 degrees. Alright, so we're going to plug that into our calculators, and you should get 15 meters per second. Alright, so that's going to be this down here, 15 meters per second. Okay? Alright, now let's go ahead and start plugging in some other stuff. We know that the acceleration in the y-axis is going to be the acceleration due to gravity. That's not going to change. But what we need to do now is figure out where the ball is. Okay? Now, since letter C here is asking me how long does it take the rocket to fall back to Earth, that means that the ball is located right here. Okay? So this y-axis information that I'm creating right now is all about the ball when it is right here at this position. Okay, so its initial velocity when the ball started out over here, still going to be 30 sine 30. The acceleration due to gravity right as the ball is striking the ground is still negative 9.81. The one other thing that we need to list is going to be our delta y. Okay, the ball started out on the ground and the ball ended on the ground, which means that delta y was 0 meters. And again, this letter C down here is asking how long does it take the rocket to fall back to Earth. So we're trying to figure out time. Alright, so let's figure out what time is. Alright. Given the information that we have right here, we need an equation that has only those 4 things and nothing else. That means no final velocity. So we're going to say delta y equals initial velocity in the y-axis times time plus 1/2 at squared. Now, if we choose to use this equation, we have to recognize that there's time here and there's time here, and that this value is 15. It's not 0, which means this piece does not go away. It doesn't cancel out. So that means we are going to end up having to use the quadratic formula. I hate using the quadratic formula. You're welcome to if you want, but I don't like it. I try and avoid it at all costs. So I'm going to actually go ahead and solve for the final velocity in the y-axis, even though they didn't ask me for that yet. And then I'm going to use that to help me figure out what the time is. Okay, so I'm going to use this equation here and solve for v final y. So that's going to be plus or minus the square root of all of this stuff here. Now, since delta y, we said, is 0, that means this whole piece right here goes away. That then means that the final velocity in the y-axis is equal to the square root of the initial velocity in the y-axis squared. Whenever you have a radical, you need to introduce plus or minus. So this means that the final velocity in the y-axis is equal to the initial velocity in the y-axis. And we need to pick, is it going to be plus or is it going to be minus? Well, since the ball is falling down in the y-axis at the end, that means that we're going to choose the negative. Okay, so this final velocity in the y-axis is equal to the negative of the initial velocity in the y-axis. Okay, so now we're going to say that the final velocity in the y-axis is equal to the initial velocity in the y-axis plus acceleration times time. And we're trying to figure out what time is. So, because we didn't want to do that quadratic formula. So time is equal to the final velocity in the y-axis minus the initial velocity in the y-axis divided by the acceleration in the y-axis. The final velocity in the y-axis is the negative of the initial velocity, so that's going to be negative 15 meters per second minus positive 15 meters per second divided by negative 9.81 meters per second squared. Alright, so when I do that, I'm coming up with 3.0581039755 seconds. Okay, now this is an actual answer, okay, so that means that we need to use the correct number of sig figs. So we used the initial velocity here in order to solve this. That means that we need 3 sig figs for our answer. So the time then is equal to 3.06 seconds. Alright, so right here for letter C, we're going to say it took 3.06 seconds for that ball to return to Earth. Okay? The next question then says, well, how far away from the original position will a rocket travel? Again, it's landed back on Earth, but if we're saying how far away from the original position, we're now in the x-axis. So if we come back here to our x-axis information, we just discovered that the time was 3.05810397555 seconds. We're not going to use 3.06 because that's rounded. Okay, and we're trying to figure out what delta x is. That was the question. All right, this time that we just plugged in here, this is the time that it took to go the whole distance. All right, so we can, maybe in this y list, I'm going to put y end so that I know that this was all the information for the end of the problem, which means that this time that I just plugged in over here is the time to get to the end. Okay, I'm just going to be very specific there because I could have a time at the maximum height or the time at the halfway point, and that's not what I have here. Okay, so we're going to be able to say that delta x is equal to the velocity in the x-axis times time plus 1/2 axt squared, right? Now, all of this goes away because the acceleration in the x-axis is 0. So that means that delta x is equal to Vx times the time it took to get to the end. Okay, so delta x then is equal to 25.980762 meters per second times 3.0581039755 seconds. Okay, so when I do this, delta x is equal to 79.45187 meters, and with the correct number of sig figs, which would be 3, because again we use this 30 initial velocity, which is what got us the Vx in the first place. So we have that there. That's going to be 79.5 meters. Okay, so the ball is 79.5 meters away. Okay, so 79.5 meters away from where it started. Okay, so then the next question there is, what is the maximum height the rocket will reach? All right, that is no longer asking about the ball when, or the rocket when it returns to Earth. It's asking about its halfway point because there's symmetry here. So its highest point is going to be the halfway point. So they're talking about the ball when it's right here. This is the new place we're talking about, and we're trying to figure out what y max is. Okay? Now, since there is symmetry to this problem, that means we're going to be able to do something that we wouldn't otherwise be able to do. Since we found out that this is the time that it takes to get to the end, and there is symmetry, we can divide that by 2, and that will tell us how long does it take the rocket to go from its starting position up to the highest point. Okay? So we can say that that's like t1/2. The final velocity up here when it gets to its highest point is going to be 0 before it starts coming back down to Earth, and we still have the initial velocity of the rocket in that y-axis is going to be 15 meters per second, and we have the acceleration. So let's make a new y list of information. We're going to do that over here. So I'm going to say that this is going to be the y at its maximum point. Okay? So the initial velocity is still going to be 30 sine 30. Okay, and that is still going to be 15. That equal sign looks like a 2. There we go, 15 meters per second. The acceleration in the y-axis is going to be negative 9.81 meters per second squared. The final velocity in the y-axis up at that highest point is going to be 0 meters per second. Okay, now, they're asking me to find delta y, or y max. Delta means final minus initial, so that's like saying y final minus y initial. The initial position is going to be the ground, which we can call 0, so that's like saying the final position minus 0, which is the final position. And that final position is that highest point, so we're going to call that y max. Okay? So I have enough information here. I have 3 pieces of information that I can use to solve for y max. So I can say the final velocity squared equals the initial velocity squared plus 2 times the acceleration times delta y. And I'm trying to solve for delta y over here, okay? So that means that delta y is equal to the final velocity squared in the y-axis minus the initial velocity squared in the y-axis divided by 2 times the acceleration in the y-axis. Okay, we could go about it this way, or you can say, oh, well, hey, I've got the time, because I can divide that whole time by 2, right? So if you do that, if that's the route that you choose to go, then you would say my initial velocity, I'm just going to make a secondary list here for if you chose to use the time. My initial velocity is still going to be the 15 meters per second. My acceleration is still going to be negative 9.81 meters per second squared. My time at the maximum point, or my halfway time, is going to be 2, or it's just going to be that other time that I have there divided by 2, okay? So instead of saying this 3.085 number, okay, we're going to divide that by 2. So I'm going to type that in my calculator real quick. All right. And then let's come plug this in over here. So I get 1.522905198775 seconds. That's how long it takes to get to that halfway point. And I'm still trying to figure out what delta y is, which is the same thing as saying what y max is. Okay? So given this setup, these variables, I would say delta y equals v initial on the y-axis times time half plus 1/2 acceleration on the y-axis times time squared. And again, this is the half time here. Okay, so you would just go through and plug in this information into your calculator for both of those and add the products up. Now, either way that you choose to do it, whether you choose to use this equation here or whether you choose to use this equation here, you're going to get the same thing, okay? It doesn't matter which one of those you use, whichever one you think is the most convenient one, go with it. Okay, so I think I'm going to use the first one that we said here. All right, so if I plug this in, I'm going to do 0 squared minus 15 squared over 2 times negative 9.81. Okay, so that's going to be 225 over, negative 225 over negative 19.62. And so that will equal 11.4678. Okay, and so with the correct number of sig figs, which is 3, that would be 11.5 meters. Again, you get the same thing if you use this method over here. Okay, so the maximum height, 11.5 meters. All right, the next question that they're asking me is, what's the velocity of the rocket, magnitude, and direction when it strikes the Earth's surface? Okay, well, when the rocket strikes the Earth's surface, that means we're back over here again, okay? So since we're back over here, let's take a look at that. When they say strikes the Earth's surface, okay, again, they're talking about this overall velocity vector. Remember that you're going to have some Vx velocity vector that's constant, and you're going to have some V final y velocity vector that you need to solve for. And we are going to need this angle theta here as well. So we are trying to figure out the magnitude and direction of this overall velocity vector. Now, fortunately for us, I decided to solve for the final velocity in the y-axis at the end. Okay, so we're looking at our information at the end, okay, and we discovered that the final velocity at the end was equal to the negative of the initial velocity, okay? So we're going to use that as our v final y. It's going to be the negative 15 meters per second, okay? And we've already done the math on that. The Vx is constant, okay? And so it's going to continue to be this, 25.98 number. We don't want to use the 26 because that's a rounded value. We want to use the whole long thing. So if we do this, it's going to be the Pythagorean theorem to find out that V final value there, okay? So that V final overall is equal to the square root of Vx squared plus V final in the y-axis squared, okay? And V final in the y-axis squared is negative 15 because it's the negative of the initial. And this Vx squared is going to be that, approximately 26 value. So if you type all that into your calculator, okay, then your V final overall should be equal to 30 meters per second. Notice that is the exact same velocity magnitude as the overall initial velocity. That's not by coincidence. That's because this problem has symmetry, okay? It's that symmetry that makes that happen. That would not be true if there was no symmetry to this problem. Now we have to get our angle theta, okay? So theta is going to be the inverse tangent of the opposite over the adjacent. Now, the opposite from this angle theta here is our y, okay? And the adjacent to our angle theta is our x, okay? So that means we're going to have the negative 15 up here, and we're going to have the, what is it, the 25.98 number. Okay, we're going to have that down here. And when you do that, you're going to get negative 30 degrees. Remember, no such thing as a negative angle. The reason that the calculator is returning a negative value is because this angle theta is below the positive x-axis here. So you can say then that the final velocity overall is equal to 30 meters per second at 30 degrees south of east, okay? Or you can set it from 0, right? And if you set this from 0, then that means that we want to know all of the angle all the way around here, okay? So that'd be 360 minus 30. So we would say, or this could be 30 meters per second at 330 degrees. We'll put that little decimal point right here to make sure that there's 3 sig figs. And so either of those right there would be the correct answer for that one. Again, that's only coming out to be 30 and 30 because of the symmetry. Alright, so we're going to say, we can plug that in here, 30 meters per second at 30 degrees south of east. Alright, the next question that we have here is, what is the vertical velocity of the rocket at its highest point? Okay, so right here when the rocket's at its highest point, what's the vertical velocity? Vertical meaning up and down. Okay, so hopefully you remember that this rocket here comes to a stop at the top. Its final velocity in the y-axis up there is 0 meters per second. Okay, so that's its vertical velocity at the highest point. Okay, so this is going to be 0 meters per second. All right, what's the horizontal velocity of the rocket at its highest point? We don't even have to do any math for that. You need to know that the velocity in the x-axis is constant. Okay, so if it was 26.0 meters per second at the beginning, then it's going to be 26.0 meters per second at the highest point, and at the end, and everywhere in between. What's the acceleration of the rocket at its highest point? Okay, well, we know that the acceleration of any projectile in the x-axis is going to be 0 meters per second squared. So there is no x-axis acceleration. That means there's only y-axis acceleration. And hopefully you remember that the acceleration is always due to gravity in the y-axis, and it's always pointing down. The acceleration in the y-axis can't be 0, okay, because then that means that this rocket would just freeze in midair. It wouldn't move anymore because the acceleration is 0. It can't be positive because then that means the rocket would always continue to go up no matter what. It would just go up forever. The reason the rocket returns to Earth, the reason that the velocity eventually comes to a stop and then the rocket turns around and comes back down, is because gravity is always pulling it down the entire time. Gravity is acting downward. Eventually, gravity wins. The rocket stops and it returns to Earth. So we can say it's going to be negative 9.81 meters per second squared. Okay, so that is all of the different questions that I could ask you. There are more, of course. I could ask you, how far away was the rocket from its original position at its highest point? That means we want delta x for the rocket when it's at its peak. Okay, so I could have you go figure out what that is. I could tell you, when the rocket is, 12 meters away from its original position, how long did it take to get there? I could, like provide you with some delta x and make you figure out what the time is. Like there's all kinds of stuff, but it's the same concept. You're just going to have an x and y list, and the y list is going to be about the ball when it is at some specific location, okay? You're always going to have an exact location of the ball or an exact time for the ball to get the when and the where. That's what you're always trying to go for, okay? All right, the last type of projectile motion problem we're going to discuss is when we are launched at an angle and we don't have any symmetry. Okay, so in this case, we've got our basketball and we're going to shoot it into our hoop over here. So we have something like that, all right? The basketball is going to start off at 2 meters above the ground, and it's going to end at 3.1 meters above the ground. Okay, so the delta y is not 0, which means there's no symmetry to this problem. Okay, so you can't just divide by 2 and stuff like we did in the previous problem. If you want to, you can't do that. Alright, let's look at some possible questions they can ask us. Alright, for this one, they're asking what's the initial velocity in the y component, what's the initial velocity in the x component, how long does it take the ball to reach the hoop, and how far away is the ball from the hoop. So you'll notice that question C and D are both referencing the hoop, so that means our y list of information is going to be about the end, okay? They could have easily asked me, what about at the ball's highest point, which is not halfway, okay? It's, could be either shifted this way or that way, we don't know. But they could ask me, how far away from its original position is the ball when it's at its highest point? Or how far above its original position is the highest point of the ball? Or how far from the ground up to its highest point is the ball? They could ask any of that stuff. How long did it take to get to the highest point? Alright, any of those things are all fair game questions. Alright, and it would just mean that you would need a separate y-axis list of information for the ball when it is at that location. As it is, as this question stands, we are being asked about the ball when it is at the end, when it's landed in the hoop, okay? So we're going to make our x and y axis list of information then, okay? X and y, and this is going to be the y at the end of the problem. So we know that the velocity in the x-axis is going to be the initial velocity of the ball, which looks to be 18 meters per second. It took off at 18 meters per second at an angle of 60 degrees. Okay, so we're going to say then that Vx is equal to 18 meters per second times the cosine of 60 degrees. And that means that the initial velocity of the ball in the y-axis is equal to 18 meters per second times the sine of 60 degrees. We know that the acceleration in the x-axis is always 0. I don't know what delta x is because they didn't give that to me, so I can't put that down. And I don't know how long it took to get over there because that's another question they're asking me. So that means that I don't know anything else in the x-axis. That's all I know right now. So time to move over to the y-axis again. We know that the acceleration in the y-axis is equal to negative 9.81 meters per second squared. We know delta y, okay, that means final minus initial, right? Its final position is 3.1 meters above the ground. Its initial position was 2.0 meters above the ground, which means that delta y is equal to positive 1.1 meters. Okay, so to answer letter A and letter B, we just need to do our trigonometry. Alright, so for the y-axis, if I do 18 times the sine of 60, I'm coming up with 15.588,457 blah 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 meters per second. Okay, now with the right number of sig figs, that's going to be 2. That means it's going to be 16 meters per second. Okay, so for letter A, we want to say 16 meters per second. Letter B is asking for the x component. let's see, we know that the cosine of 60 is 0.5, so that's half of 18, so that's going to be 9 meters per second. Of course, if you didn't know the 0.5 thing, you can type it in your calculator, you'll get the same thing. So 9.0 meters per second, so that we've got the right number of sig figs. Now we need to figure out how long does it take the ball to reach the hoop. Well, on the x-axis, I only have 2 pieces of information, and in the y-axis, I have 3 pieces of information, which means I need to use the y-axis to calculate my time to get to the hoop. Okay? So I could use my delta y equals VOT plus 1/2 AT squared, but if I do that, I'm going to have to use the quadratic formula. And remember, I don't like using quadratic formulas. So instead, I'm going to solve for the final velocity in the y-axis first, and then I'm going to use that to find time. So the final velocity in the y-axis squared equals the initial velocity in the y-axis squared plus 2 times acceleration times delta y. We need to make sure we have a plus and a minus, and since the ball is falling down at the end, this is going to be the minus when we get done with all this. So that's going to be that 15 number from up above, 15.588, so on and so forth, meters per second. Square that plus 2 times negative 9.81 meters per second squared. Times 1.1 meters. So the final velocity in the y-axis is equal to negative 14.8801200967 meters per second. I'm just including several digits. Okay, then we're going to say that the final velocity in the y-axis is equal to the initial velocity in the y-axis plus acceleration times time, and we want to solve for time, and of course this is at the end. Okay, so time at the end is equal to final velocity minus initial velocity over acceleration. So that's going to be this negative 14 number from up above minus the 15 number and divide all that by the acceleration due to gravity. Okay, so I'm coming up with 3.1058691 seconds. So with the proper number of sig figs being 2 because of the 18 meters per second at the beginning, we get 3.1 seconds. Okay, so how long does it take the ball to reach the hoop? That's going to be 3.1 seconds. The last question asks how far away is the ball from the hoop? Okay, so that's an x-axis question. All right, so I can take that time that I just figured out and put that over here because time is a scalar, so it belongs in both the x and the y axis. So I'm going to go ahead and bring that time and put that over here. And I'm using the big long number, not the rounded version. And I'm trying to figure out what delta x is. Okay, so we can say delta x is equal to bx times t plus 1/2 ax t squared. The acceleration in the x-axis is always 0, which means this whole term over here goes away. So delta x then is going to be equal to 9 meters per second times the 3.105 value for time. Okay, so when I do that, I'm coming up with delta x is equal to 27.952 meters. We want 2 sig figs. This 9 here is going to do some rounding, so that means we've got 28 meters. So if I come back up here, then we can say the ball is 28 meters away from the hoop, or from the launch position when it lands in the hoop. All right, so those are just 4 basic questions. Again, I could ask you a whole bunch of other ones, and the way to answer that would be the same as we've done here. You would need an x-axis piece of information, and you would need y-axis information. The y-axis information may be at the end when it lands in the hoop, or it may be at its maximum height, or it may be at some other point in between, depending on what information I'm giving you or what information I'm asking for. The point is, you just need to be able to list your x-axis and your y-axis information. Okay, the last thing that I need to talk about is that range equation that I referenced in our organizational tree earlier. When we say range in physics, we mean delta x. That's what range is. So the range equation says that delta x is equal to the initial velocity squared times the sine of 2 theta over positive little g. Okay, now let's talk about this real quick. This initial velocity here is the overall initial velocity. It is not the decomposed x velocity or the decomposed velocity in the y-axis. It's that overall initial velocity that they gave you. Okay, 2 theta means you literally multiply the angle that they give you by 2. And then little g is not negative, okay? Remember that little g is positive. And so that this would be a positive 9.81 meters per second squared here. Now, the only catch with the range equation is that it only works if delta y is 0, okay? In other words, there has to be symmetry present. Okay, there must be symmetry present for the range equation to work. So let's say that we go back to our rocket question real quick, okay? Because that rocket had symmetry. It was going to land back on Earth, right? Okay, so let's say that we want to know what delta x is about where the rocket lands when it comes back to Earth. Remember, we actually answered this question previously in this video, and we had to go figure out what the time was for the rocket to land over here using the y-axis list of information, and then we took that and plugged it back into the x-axis information. We had to decompose the overall vector and then we had to solve for delta x. We're going to do it again using this range equation though, and you'll see that it's a huge time saver. All right, so we're going to take the 30 meters per second and we're going to square that. Times the sine of, now the angle they gave me is 30 degrees, 2 times 30 is 60. And divide all of that by positive little g, so 9.81 meters per second squared. Okay, so when I do that, I'm coming up with 79.45187 meters. So with the correct number of sig figs, which would be 3, I'm going to end up with 79.5 meters, which is the exact same thing as we ended up with earlier in the video when we had a lot more steps to go through. Okay, so this range equation can definitely solve you a bunch of time. You just have to remember it only works if you have symmetry. Okay, only works if there's symmetry. All right, I hope that you found this easy to follow and that you took notes with me as we went along. And if you have any questions over anything that I did here that you didn't quite understand, please come see me for tutorials, and I'll be happy to go over it with you and clarify anything that you didn't understand. As always, thank you for learning with me today, and I will see you next time.